It is after dawn on a freezing December morning at London Euston. Frost clings to the platform edges, and a crowd of journalists and engineers presses toward a train unlike anything British Rail has run before. Low, sleek, oddly futuristic against the soot-stained Victorian roof above it, the train looks like it belongs to a different decade. Cameras flash. Engineers check instruments with pride. The assumption in the air is simple. Britain has finally built something to rival Japan's bullet trains. Within hours, that assumption collapses. Something inside the train's most advanced system is already failing, and the most expensive machine in British rail history is about to be humiliated in front of the press, invited to watch it succeed. The train is called the Advanced Passenger Train, the APT, and by the time it rolls out of Euston on December 7th, 1981, it has already eaten 20 years of research and hundreds of millions of pounds. The pitch behind it is almost embarrassingly elegant. Instead of ripping up Victorian-era curved track and laying brand new, straight high-speed lines, the way Japan and France were doing, British engineers asked a different question. What if the train itself could solve the problem the track creates? So they built a train that tilts. Carriages lean into curves like a motorcyclist leaning into a turn, computer-controlled hydraulics reading the track ahead and adjusting in real time. No new infrastructure, no decades of construction. Just a smarter machine running on the same old rails. On paper, it is the cheaper, cleverer solution. This wasn't a rushed idea bolted together overnight. The first experimental prototype had run on test track years earlier, powered by gas turbines pulled straight out of helicopter engineering, before British Rail moved to an electric production version. In 1979, that prototype broke the British rail speed record, a record that stood for years afterward. By every technical measure available before December 1981, the APT looked like a success story already in progress. The press knew that history. That's exactly why the cameras were there. Here's the part most people miss. The obvious assumption is that faster trains need straighter, newer tracks. That's the Japanese model, that's the French model, and it makes intuitive sense. More speed needs more room to turn. The APT's entire reason for existing was to prove that assumption wrong, to show that with enough engineering cleverness, a train could beat geometry itself. And for a while, it actually worked. In testing, the APT hit a British rail speed record that stood for decades. The tilt math was sound. The physics checked out, which is exactly why what happened next felt so confusing to everyone watching. Here's what's actually happening when a train tilts. As a train rounds a curve at high speed, lateral force pushes passengers sideways, the same sensation as a car cornering hard. A normal train can't go fast enough through tight curves without spilling drinks and unsettling stomachs. So the APT's hydraulic actuators read the curvature ahead and lean the carriage body inward, canceling out that sideways force before passengers even feel it. It's elegant. It's also incredibly sensitive equipment, full of seals, valves, and fluid that all have to behave with total predictability, reacting correctly within fractions of a second at speeds where a wrong correction is felt instantly by everyone on board. And on the morning of December 7th, 1981, the temperature outside drops well below freezing. That's the first hard twist. Cold doesn't just slow things down. It changes how hydraulic fluid behaves, how seals contract, how sensors read. The very system designed to make the ride smoother than anything British Rail had ever offered starts behaving erratically. Instead of tilting in sync with the curve, the carriages lurch out of phase with the train's actual motion, tilting the wrong way at the wrong moment. Passengers don't get a smoother ride. They get the train equivalent of seasickness. And the people experiencing it aren't ordinary commuters, they're journalists, deliberately invited on board to witness Britain's rail triumph, now gripping armrests and turning green in front of each other. And the tilt mechanism wasn't even the only thing the cold attacked. The same low temperatures that confused the hydraulics also affected brake components and door mechanisms elsewhere on the train, the kind of compounding small failures that rarely make headlines individually, but stacked together on one trip in front of one specific audience read as total system collapse. One glitch is a footnote. 3 glitches on the same freezing morning, with reporters already reaching for notebooks, becomes a story that writes itself. This is where scale changes everything. This isn't a faulty bolt on a freight wagon nobody notices. This is the literal flagship of British rail engineering, on its first paying passenger journey, malfunctioning in front of the exact audience assembled to broadcast its success nationwide. 2 decades of research, public money, national pride wrapped up in beating Japan and France at their own game. And it's failing in real time with reporters scribbling notes that will run in every major paper within hours. A failure on a quiet weekday freight run gets fixed and forgotten. A failure broadcast nationally on the one day that mattered most becomes the story the entire project is remembered for, regardless of how many years of solid engineering came before it. Underneath the embarrassment sits a quieter, messier story. British Rail wasn't just racing foreign engineers, it was fighting for its own survival. Government funding for nationalized rail was already under political pressure, with critics asking why taxpayers were bankrolling a state-run railway at all. The APT was meant to be the answer. Glamorous proof that public investment in rail could outperform private alternatives elsewhere. Engineers inside the project had flagged cold weather vulnerabilities during testing. The fluid behavior in low temperatures wasn't a total surprise, but canceling the launch would have meant admitting publicly that the program wasn't ready, after years of promises to politicians who controlled its budget, and after journalists had already been booked onto the very train now sitting in the depot. And here's the paradox. Ordinary instinct says that if a flaw is suspected, the train shouldn't run in front of journalists in freezing weather. Delay it. Protect the reputation. But that instinct, the safe one, is exactly the one professional engineers had reason to override. Laboratory tests and short test runs can only reveal so much. Some failure modes only appear under full operational stress. Real passengers, real schedules, real weather extremes, sustained at full speed for hours. Pushing forward into a real revenue run, even with known risk, was in some ways the only way to actually find out where the system broke. The decision that looks reckless in hindsight was also the only decision that could generate the proof British Rail desperately needed, one way or the other. This is the uncomfortable truth behind a lot of engineering history. Controlled testing shows how a system behaves when everything around it is managed. It almost never shows how a system behaves when it meets real weather, real fatigue, real schedule pressure, and a few hundred ordinary passengers at once. Aircraft manufacturers learned this the hard way with early flight testing. Shipbuilders learn it with maiden voyages. Rail engineers on that morning in 1981 learned it on live television and in the next day's front pages. December 7th, 1981 became that proof, and not in the direction anyone wanted. The London Euston to Glasgow Central run was the APT's first and only revenue passenger service. By the time it returns, the story is already written. A humiliating, nausea-inducing failure aboard Britain's most expensive train, witnessed firsthand by the press corps invited specifically to praise it. Within days, British Rail quietly withdraws the APT from passenger service. It never returns to carrying paying passengers again. 20 years of engineering effort effectively ends with a single bad morning, and a project that had survived multiple changes of government, multiple funding reviews, and a national speed record could not survive one freezing commute with the wrong people watching. Now look again at something that's been hiding in plain sight the entire time. Anyone who has ridden a modern tilting train in the UK, in Italy, anywhere across more than 10 countries today, has felt this exact technology working perfectly. Those trains slightly slow and lean into curves, and most passengers register it as nothing more than a faint sway, dismissed as just how trains feel. That sway is the APT's ghost. The concept that supposedly failed in 1981 didn't disappear. It got licensed instead to the Italian manufacturer Fiat, who took the underlying tilt research, refined the hydraulics, fixed the cold weather sensitivity, and built what became the Pendolino, now one of the most widely used tilting train designs in the world. Notice what changed between the two versions. Modern tilt systems use accelerometers and onboard computers that constantly cross-check the train's actual motion against what the curve geometry predicts, correcting in fractions of a second instead of relying on a single sensor reading. They tilt by smaller amounts, more conservatively, with redundant systems designed specifically to fail safely rather than fail violently. Every uncomfortable lurch British Rail's engineers experienced in 1981 became a design rule written into someone else's blueprint a few years later. The failure didn't kill the idea, it edited it. It's worth being precise here because the real story isn't quite as clean as British engineers were geniuses and bureaucrats ruined it. The APT's tilt concept was genuinely sound, but the program also suffered from underfunded testing schedules, shifting political priorities across multiple governments, and a rushed timeline driven by the need to show results. Different eras of British rail policy treated the project with wildly different levels of commitment. Some of the failure really was technological immaturity. Some of it was institutional impatience. Most breakthrough engineering fails its first real test, not because the core idea is wrong, but because it gets exposed to real-world conditions before the supporting systems around it are mature enough to survive contact with reality. It's also worth noting that not every tilting train today is the APT's direct descendant, and not every country adopted tilt technology the same way or at the same pace. Some operators favor it heavily on winding routes where it saves real time. Others, running mostly on straighter modern lines, get little benefit and skip it entirely. The technology isn't a universal upgrade, it's a tool that solves one very specific geography problem, the exact problem the APT was originally built to solve on Britain's own curved Victorian-era network. So Britain ends up in a strange position. It invented the tilting train. It proved the concept could work, set a national speed record doing it, and then shelved the entire program rather than fix it. Decades later, British train operators lease and run Pendolino trains, the very technology that traces directly back to the APT, except now built by an Italian company that took the idea Britain abandoned and made it work. The country that banned the technology ended up importing it back with someone else's name on it, paying for the privilege of using a fixed version of its own invention. Which raises a bigger, stranger question worth sitting with. The APT wasn't the only ambitious British engineering project that got shelved domestically only to prove itself somewhere else, or decades later. Concorde, early hover train research, several maglev prototypes all carry some version of the same pattern. Extraordinary engineering, undone less by physics than by timing, funding, and institutional nerve. Sometimes the most advanced machines aren't too early for the technology to support them. They're too early for the people running them to trust what the engineering is actually telling them. And that pattern keeps reappearing in places passengers never think to look. Modern railways now run predictive sensors along the track itself, constantly feeding temperature, vibration, and wear data back to control centers long before a human would notice anything wrong. The freezing morning that ended the APT is, in a strange way, the reason those systems exist at all. A single public failure that quietly rewired how an entire industry decides what's actually ready to carry passengers. Once that gap becomes visible between what a machine can technically do and what the system around it is actually prepared to trust, it starts showing up almost everywhere in the engineered world, waiting for the next uncomfortable question to be asked.